Look up on a clear winter night, find the constellation Orion, and trace your eye to the upper left. That ruddy, copper-burning point of light is not a planet. It is not a nearby object. It is a dying star so vast that if you placed it at the centre of our own solar system, its surface would swallow Mercury, Venus, Earth, Mars, and reach almost to the orbit of Jupiter. And for about 4 months between late 2019 and early 2020, it began to go dark, not dim, dark. The kind of darkness that made professional astronomers abandon their scheduled observing programs and turn every available telescope toward the constellation of the Hunter, with the particular urgency of people who suspect they are about to witness something that has never been seen before. Was this the last gasping signal of a star preparing to die? Was a supernova, one bright enough to cast shadows on Earth in the middle of the night, finally, after centuries of waiting, about to ignite? The answer, when it came, was stranger than anyone had imagined, and it did not come alone. Buried inside the explanation for the dimming was a second secret, one that had been hiding in plain sight for longer than modern astronomy has existed. And that secret changes everything we thought we understood about one of the most famous stars in the human sky. There is a particular kind of intimacy in the relationship between Betelgeuse and our species. It is not a relationship we chose exactly. It is one the star imposed upon us by virtue of its sheer relentless visibility. On any clear winter night, from almost anywhere on Earth where light pollution has not yet devoured the sky, you can find it without a chart. It is in the shoulder of Orion, that great swagger of a constellation, most recognizable pattern in the northern sky, and it glows with a colour that is unlike anything else up there. A warm, deep, coppery red that suggests heat and age in the same breath, the colour of a dying fire when the flames have become embers. Humans have been watching this star for as long as humans have been watching the sky. The ancient Egyptians knew it, the navigators of Polynesia used it. The Kokatha people of the Great Victoria Desert in Australia tracked its brightening and dimming with a precision that would not be equalled in the Western astronomical tradition for centuries. Medieval Arab astronomers mapped it with such care that the name we use today, Betelgeuse, is derived from the Arabic Yad al-Jawza, meaning roughly the hand of Orion, a name that reached European astronomy through a series of transcription errors that compressed and transformed it across languages until it arrived in our lexicon in its current, slightly comic form. That chain of mistranslation, incidentally, is why the star now shares a name with a 1988 Tim Burton film. This is not the universe's fault, but what is the star exactly beyond a point of ruddy light? To understand why its recent behaviour was so alarming, you need to understand what kind of object it actually is. Because Betelgeuse is not a star in the way our Sun is a star. Our Sun is, in the grand catalogue of cosmic objects, a modestly sized, middle-aged yellow dwarf, competent, reliable, unremarkable in the way that gets you a long and stable life. Betelgeuse is something else entirely. It is a red supergiant, a category of star that exists at the outermost boundary of the possible. It has exhausted its original hydrogen fuel and swollen to a size that defies any intuitive sense of scale. Its radius is approximately 700 times that of our Sun. Measured in raw numbers, our Sun spans roughly 1,391,000 kilometres from one edge to the other. Betelgeuse, at its current size, spans something in the range of 975,000 kilometres. If you placed it where our Sun sits, its visible surface would swallow every rocky planet in the inner solar system without pausing for breath, and its outer atmosphere would reach nearly to the orbit of Jupiter, 778 million kilometres from where its heart would be. Its mass is estimated at somewhere between 16.5 and 19 times the mass of our Sun, which means it has paid for its extraordinary size with an equally extraordinary burn rate. The physics of stellar evolution are, at their core, a negotiation between two forces: the outward pressure generated by nuclear fusion in the core, pushing against gravity's relentless inward pull. The more massive a star, the more violently its gravity squeezes the core, the hotter the fusion becomes, the faster the fuel is consumed, A star like our Sun can burn hydrogen steadily for approximately 10 billion years. Betelgeuse, by contrast, has already lived through perhaps 8 to 11 million years, and it burned through its core hydrogen in that time, with the extravagance of a bonfire compared to the Sun's candle. Now it is burning helium in its core, with a thin shell of hydrogen fusion still burning around it, and the layers of heavier elements piling up toward an interior that is edging, stage by stage, toward the conditions for carbon burning, oxygen burning, silicon burning, and finally the formation of an iron core, at which point fusion stops, gravity wins, and in the space of a fraction of a second, the entire star collapses and then explodes. This is the destination toward which Betelgeuse is travelling. The question that has defined modern observational study of this star is not whether it will arrive there, but when. Its distance from Earth is a number that has been revised repeatedly, which is itself a small story about the difficulty of measuring the universe's dimensions. For much of the last century, estimates placed Betelgeuse at somewhere between 430 and 700 light-years away. A 2020 study, incorporating new modelling alongside interferometric data, revised the figure to approximately 548 light-years, suggesting it was 25% closer than the previous consensus. More recent work has settled on a distance closer to 700 light-years. The uncertainty is not a failure of science. It reflects the genuine challenge of measuring the parallax of a star whose outer atmosphere is so vast, so turbulent, and so irregular that pinning down its geometric centre requires heroic statistical effort. The number matters, though, because it determines how bright a Betelgeuse supernova would appear in our sky when the time comes, and it determines how the star's true luminosity compares to models of stellar evolution, a question that, as we will see, carries stakes far higher than mere calibration. What we do know is that Betelgeuse is among the most luminous stars in the Milky Way. Its luminosity is roughly 100,000 times that of our Sun. It emits light across a vast range of wavelengths, most of it in the infrared, and the light that reaches our eyes, that warm copper glow in Orion's shoulder, represents a fraction of its actual output. Because of its size and luminosity, Betelgeuse is also the only star other than the Sun that has been directly imaged in sufficient resolution to reveal surface features. Hubble Space Telescope observations as far back as 1995 revealed a mottled, boiling surface dominated by convection cells, enormous columns of rising hot plasma, of a size and scale that has no solar equivalent. On our Sun, convection cells are roughly 1,000 kilometers across. On Betelgeuse, a single convection cell can span more than 60% of the star's entire radius. The surface of this star does not shimmer, it heaves, and then, in October 2019, something on that heaving surface broke loose. The American Association of Variable Star Observers, the AAVSO, is one of the oldest and most disciplined citizen science organizations in the world. Since 1911, its members have been systematically measuring the brightness of variable stars, building an archive that now encompasses more than 50 million individual observations. Betelgeuse has been one of their most consistently monitored subjects for the simple reason that it varies. It has always varied. Astronomers have known since at least the 1830s that Betelgeuse is not a fixed beacon, but a pulsating engine, swelling and contracting, brightening and dimming, on a cycle of approximately 400 days. This rhythm is not perfectly regular, it is semi-regular, influenced by the star's complex internal dynamics, but it is recognizable and consistent, a heartbeat that observers had come to rely upon. So when the October 2019 AAVSO data showed the star beginning to drop in brightness, nobody panicked. Stars do this. Betelgeuse does this. The 400-day pulsation cycle had seen it dim before, and it always recovered. The observations were noted, logged, and filed with the calm efficiency of a system that has been noting, logging, and filing variable star data for well over a century. By November, the unease began to build. The drop was steeper than the models suggested for a normal pulsation minimum. By December, when ground-based telescopes confirmed that the star's southern hemisphere was dimming conspicuously, not uniformly, but asymmetrically, with one quadrant of the disk fading faster than the rest. The astronomical community began to pay closer attention. By mid-January 2020, Betelgeuse had fallen from its typical visual magnitude of roughly 0.5, where it normally sits as one of the 10 brightest stars in the sky, to a magnitude of approximately 1.0. That is not a trivial change. In the logarithmic scale that astronomers use to measure stellar brightness, each unit of magnitude corresponds to a factor of roughly 2.5 in actual brightness. Betelgeuse was already measurably, undeniably dimmer to the naked eye. By mid-February 2020, it reached its floor, a visual magnitude of approximately 1.614, the faintest it had been in over 150 years of recorded photometric data. It had lost, relative to its normal brightness, more than 2/3 of its visible light output. In the constellation Orion, where Betelgeuse is traditionally the second brightest star after Rigel at the opposite corner, it had dropped below the star Bellatrix, which normally sits well below it in the celestial hierarchy. Orion's shoulder had gone quiet. This was when the wider world noticed, and the interpretation that seized the public imagination was, of course, the one that was most dramatic. Betelgeuse was about to explode. The word supernova appeared in mainstream news articles alongside phrases like visible in daylight and as bright as the full moon. Social media amplified the speculation with the particular enthusiasm it reserves for events that are simultaneously catastrophic and entirely beyond anyone's control. Astronomy forums and preprint servers buzzed with discussion. Observation requests flooded into telescope scheduling systems from researchers who had been working on entirely different problems and suddenly found themselves reluctant to spend their allocated time anywhere but the shoulder of Orion. The professional astronomical community was, it should be said, considerably more measured in its public pronouncements. The star's behaviour was unprecedented in the modern observational record, and unprecedented is a word that carries real weight in a field built on pattern recognition. But the mechanism of a core collapse supernova is not something that produces days or weeks of warning dimming from the outside. A star does not gently fade before it explodes. The final collapse happens on a timescale of milliseconds, the bounce takes seconds, and the shockwave emerges into the stellar envelope within hours. What observers on Earth would receive first would not be a dim star but a burst of neutrinos, detectable only by purpose-built underground detectors, followed by a rapid, violent brightening as the expanding shockwave lit up the star's outer layers. The dimming observed in late 2019 was, in almost every model anyone had constructed, the wrong shape for a pre-supernova signal. But almost every is not the same as every, and no one, in the honest reckoning of the science, had ever watched a star go supernova in real time from a front row seat 700 light-years away. As Andrea Dupree of the Harvard-Smithsonian Center for Astrophysics would later say, carefully, precisely, no one knows what a star does right before it goes supernova, because it's never been observed. There were competing explanations on the table. The first proposed that the dimming was caused by a giant cool star spot, a dark patch analogous to a sunspot, but covering a significant fraction of the visible disk. The second proposed that the star's atmosphere had cooled locally, reducing the output of visible light, while maintaining normal behaviour in other wavelengths. The third proposed that something external had formed between the star and Earth, a cloud of dust, generated somehow from the star itself, that was selectively blocking visible light, while remaining transparent at other wavelengths. Each hypothesis had advocates. Each made different predictions about what further observations would reveal. What nobody initially appreciated was that all three were partially right, and that the truth connecting them was more violent, more unprecedented, and more consequential than any single hypothesis had anticipated. Because the question of why Betelgeuse dimmed was not, it turned out, separable from the question of what had happened inside the star in the weeks and months before the dimming began. And what had happened inside the star was this: Betelgeuse blew its top. This is the moment where the story stops being about a star that dimmed and starts being about a star that did something no normal star had ever been observed doing. A convective plume, a column of superheated plasma rising from deep within the star, possibly more than 1,000,000 miles across, punched through the stellar atmosphere with enough force to eject a piece of the star's visible surface into space. Not a thin outer wisp of corona, not a tenuous stream of stellar wind. A piece of the photosphere itself, the actual surface of the star. There is no solar analogy that fits this event. Our Sun regularly produces coronal mass ejections, CMEs, which are eruptions of magnetized plasma from the corona. They are powerful enough to disrupt satellite communications and fry electrical grids when they impact Earth's magnetosphere. A particularly energetic solar CME might carry a mass of roughly 10 billion tons of material, the surface mass ejection. The SME, as it has now been classified to distinguish it from its solar cousin, that Betelgeuse produced in 2019 expelled approximately 400 billion times as much mass as a typical solar CME. 400 billion times. The fractured chunk of photosphere that tore free from the star's surface and travelled outward into space weighed several times as much as our Moon. But even that staggering number did not fully reveal the consequences of what had happened. Because the ejection was only the beginning of the event. What came next was the dust, understanding the great dimming required in the end, a 4-panel answer to a question that had seemed like it might have a single-panel solution. Each panel added a layer of complexity, and the final panel pointed not at a resolution, but at an entirely new mystery that made the dimming event look, in retrospect, like the visible surface of something far deeper. The chain of causation, as reconstructed from data collected by the Hubble Space Telescope, the European Southern Observatory's Very Large Telescope, the ALMA Radio Interferometer Array in the Atacama Desert, the Stellar Robotic Observatory, the Tillinghast Reflector Echelle Spectrograph, and the systematic visual monitoring of the AAVSO, runs as follows. Somewhere in the months before October 2019, a convective cell of extraordinary size and energy churned its way upward through Betelgeuse's interior. Betelgeuse's surface is dominated, at any given time, by somewhere between 2 and 3 of these enormous convection cells, each one an upwelling of hot material that rises, spreads, cools and descends, driven by the same basic physics as the convection cell in a pot of boiling water, only operating on a scale that would encompass entire planetary systems. By September 2019, the Hubble Space Telescope's ultraviolet spectroscopic instruments, which were conducting routine monitoring of the star as part of a 3-year program, began detecting something unusual in the southern hemisphere of Betelgeuse. Dense, heated material was moving through the star's atmosphere at approximately 320,000 kilometers per hour, or about 200,000 miles per hour. This was not normal stellar wind behavior. This was something with urgency and mass behind it. In October and November, the movement continued and accelerated. In December, the ground-based observations confirmed the asymmetric dimming. By January, it was clear to everyone watching. The Hubble team, led by Andrea Dupree, later described what they saw in September through November 2019 as material that was 2 to 4 times more luminous than the star's normal brightness. A hot, bright extrusion of material moving outward from the southeast quadrant of the star's surface. The key word in that description is southeast. The dimming that followed was also concentrated in the southern hemisphere. The spatial correspondence was not coincidental. What happened next was governed by thermodynamics. As the ejected plasma rose away from the star's surface and moved outward into the cold darkness of the stellar atmosphere, it expanded. Expanding gas cools. The temperature of this material, which had been several thousand degrees Kelvin at the photosphere, dropped as it travelled. And somewhere in that cooling curve, at a temperature in the neighbourhood of 500 Kelvin, a phase transition occurred. The gas condensed into solid particles, silicate dust grains essentially. A cloud of tiny mineral crystals formed from the material of a star's own surface assembled itself in space and drifted outward, positioning itself, from Earth's perspective, between the observer and the star's disk. This is the dust veil explanation, confirmed definitively by a 2021 study in Nature, led by Miguel Montages of the Paris Observatory, who had been using the Very Large Telescope's SPHERE instrument to directly image Betelgeuse's disk at high resolution throughout the event. The study showed the star's southern hemisphere partially obscured by material that was consistent in its thermal and optical properties with silicate dust. The cloud was estimated to cover roughly 1/4 of the star's visible disk as seen from Earth. 1/4 of the disk of a star 700 times the size of our Sun, obscured by the star's own expelled surface material. The great dimming was not the star dying, it was the star bleeding. But here is where the story complicates itself in a way that took months and then years to fully appreciate. The dust cloud explained the dimming. It did not explain why the convective plume was so energetic. It did not explain what role the star's own pulsation cycle played in the ejection event. And it absolutely did not explain what happened after the star recovered. Betelgeuse's 400-day pulsation is not merely a brightness variation. It is a physical oscillation, the entire star expanding and contracting, its outer layers rising and falling like the surface of a breathing organism. This pulsation is driven by what astrophysicists call the Kappa mechanism, a process in which certain layers within the star periodically trap outgoing radiation, heat up and push outward, then cool and fall back, creating a regular driving force for the oscillation. It is a genuine rhythm, as measurable and as consistent as a heartbeat. For almost 200 years, or more precisely, for as long as systematic photometric and spectroscopic monitoring has existed, astronomers had used the Betelgeuse pulsation as a calibration standard and as a diagnostic tool for the star's interior dynamics. After the surface mass ejection of 2019, the heartbeat stopped not permanently, but the 400-day pulsation cycle, which had governed observations of Betelgeuse since the 1830s, became scrambled, disrupted, unreliable in the years following the Great Dimming. Dupree's description of the aftermath: "The interior is sort of bouncing," she said, with a slightly stunned expression of someone trying to describe something that has no precedent, captures the observational reality. The star's internal convection cells, she suggested, might be sloshing around like an imbalanced washing machine during its spin cycle, unable to recover their synchronized rhythm because the departure of a piece of the photosphere had fundamentally altered the internal pressure distribution. The surface was rebuilding itself. The photosphere was reforming, but the restoring forces were fighting against an internal dynamic that had been violently perturbed, and the result was a star that was, in a quantifiable sense, out of beat. This disruption also revealed something else that had been hidden inside the 400-day pulsation cycle, a second, much longer period of variability. Betelgeuse does not have one heartbeat, it has two, and the second one, the one that the disrupted pulsation cycle threw into sharp relief in the years following the Great Dimming, is something that the astronomical community had known about for decades without being able to satisfactorily explain. It is called the long secondary period, and its apparent duration is approximately 2,170 days, or just under 6 years. And it is, I want to be precise here, almost certainly not a property of the star itself. This is the Betelgeuse secondary period problem, and it had been lurking, unresolved, in the observational data for longer than most of the researchers who are currently working on it have been alive. The difference between a pulsation period and a long secondary period is not merely a matter of timescale. It reflects fundamentally different physics. A pulsation period, like Betelgeuse's 400-day cycle, is an intrinsic property of the star, a consequence of its mass, radius, temperature, and internal structure. You can calculate from first principles what a star of Betelgeuse's parameters should pulsate at, and the answer broadly matches the observed 400-day rhythm, which is reassuring. The long secondary period, at roughly 2,170 days, does not fit any standard model of radial pulsation for a star with Betelgeuse's known properties. It is too long, and its amplitude does not match the predictions. When theorists tried to model it as a pulsation, they consistently found that the radius you needed to generate a 2,170-day fundamental mode was incompatible with the measured angular diameter of the star. There was a contradiction at the heart of the number, and contradictions in astrophysics do not dissolve on their own. They either demand new models, or they demand explanations from outside. For years, the dominant explanation was vague. The long secondary period was categorized as an oscillation of uncertain origin, possibly related to large-scale convective overturn, possibly related to non-radial oscillation modes, possibly a statistical artifact of the limited observational baseline. It was, in the politely evasive language of scientific literature, when confronted with genuine uncertainty, not well understood. Then the dimming event arrived, the pulsation rhythm broke, and what had been background noise suddenly became the loudest signal in the data. And two independent research groups, working separately with archival data that stretched back over a century, arrived at the same conclusion at nearly the same time. The long secondary period of Betelgeuse is not a property of the star, it is the signature of something orbiting the star. Something that had been invisible, undetected, and completely unsuspected for the entire history of modern stellar astronomy. Betelgeuse, the astronomers concluded, was not alone. To understand why the companion hypothesis took so long to reach a consensus, you need to understand just how counterintuitive it is. Betelgeuse has been one of the most intensively observed stars in the sky for the entirety of modern astronomy. It is the only star other than the Sun for which Hubble has been able to directly resolve surface features. It has been studied in radio wavelengths by ALMA, in ultraviolet by the Hubble Space Telescope, in visible light by dozens of ground-based observatories on every inhabited continent. Every unusual behaviour it has ever displayed has been scrutinised by some of the most capable astrophysicists in the world. And through all of that observation, through all of those decades of careful measurement, the companion had stayed hidden. This is not a failure. It is a lesson in how difficult the universe can make it to find a thing when the thing is located directly next to one of the brightest, largest, most luminous objects in your field of view. Betelgeuse emits approximately 100,000 times the luminosity of our Sun. Its angular diameter in the sky, at a distance of roughly 700 light-years, is approximately 55 milliarcseconds, which is large enough for direct surface imaging by the best existing instruments. But anything orbiting close to Betelgeuse would be immediately, catastrophically outshone by the star itself. Finding a companion star embedded in the extended atmosphere of Betelgeuse would be, in the words of Anna O'Grady of Carnegie Mellon University, confronting an absolutely insane brightness difference. The star and its companion, she noted with considerable restraint, presented a brightness difference between Betelgeuse and this little companion that pushed current detection technology to its absolute limit. The evidence for the companion's existence arrived not from imaging, but from the mathematical precision of what the observations required. The argument proceeded in three independent lines, each pointing to the same conclusion from a different direction. The first line came from the long secondary period itself. A 2025 study by Morgan McLeod and colleagues at the Harvard-Smithsonian Center for Astrophysics analysed more than a century of Betelgeuse's radial velocity data, visual magnitude measurements, and astrometric positions, every measurement available from the entire history of systematic Betelgeuse observation. Their analysis found that the 110-day long secondary period appeared not only in the brightness data, but also in the star's radial velocity and in its astrometric position, its actual position on the sky. This is important because a purely internal oscillation would not cause a star to shift its position. An orbiting companion would, through gravitational reflex motion, cause the star to trace a small ellipse around the system's common centre of mass. The astrometric signal was consistent with a companion of approximately 1 solar mass orbiting at roughly twice Betelgeuse's radius. Or, to put that in terms that carry physical weight, orbiting at approximately 4 times the Earth-Sun distance, which places the companion almost certainly within Betelgeuse's extended outer atmosphere. The second line came from an entirely different direction, the star's rotation. In 2024, new observations using ALMA found that Betelgeuse's projected rotation rate was approximately 5 kilometers per second, 2 orders of magnitude faster than single-star evolutionary models predict for a red supergiant of this age and mass. When a star evolves off the main sequence and expands into a red supergiant, conservation of angular momentum dictates that its surface rotation should slow dramatically, in the same way that a figure skater spinning with arms extended rotates more slowly than one with arms pulled in. A star expanding to 700 solar radii should be barely rotating at all by surface standards. At 5 km/s, Betelgeuse is spinning significantly faster than it has any right to. The most natural explanation is that angular momentum has been transferred to it from an orbiting companion through tidal coupling, spinning it up over millions of years the way a small moon can, over geological time, alter the rotation rate of its parent planet. The third line came from the far ultraviolet. A 2025 Hubble Space Telescope study led by Jared Goldberg and colleagues used the Space Telescope imaging spectrograph to search for the spectral signatures of a companion in Betelgeuse's ultraviolet output. Their astrometric evidence suggested an edge-on binary orbit aligned with Betelgeuse's spin axis, a geometry that is consistent with a long period of tidal interaction between the two objects, which would naturally tend to align the orbital and rotational angular momenta over time. Taken together, these 3 independent lines of evidence, the long secondary period in photometric, radial velocity, and astrometric data, the anomalous rotation rate of the supergiant, and the ultraviolet spectroscopic constraints, converged on a picture that was difficult to deny. Betelgeuse has a companion, orbiting in a 2,110-day period at a distance of approximately 4 astronomical units, with a mass between roughly half and 1.5 solar masses. I will be honest about what I find remarkable here. This is not a faint theoretical possibility extracted from a single marginal dataset. This is a conclusion supported by more than a century of accumulated observational evidence derived independently from 3 different observational techniques, pointing to the same object. The companion was there in the 19th century radial velocity data. It was there in the 20th century photometric record. It was there in the 21st century astrometry. Every measurement ever made of Betelgeuse contained, in retrospect, a signal that said, "You are not looking at one thing." And for more than 100 years, the signal was there, and nobody found it. Not because the scientists were careless, but because the star itself is so overwhelmingly dominant that it buries everything in its vicinity under an ocean of light. But once the hypothesis was on the table, it did something elegant. It explained the behaviour. The 2,110-day long secondary period, which had stubbornly resisted every attempt to model it as an intrinsic stellar oscillation, made perfect physical sense as an orbital period. When the companion is at its closest approach to Betelgeuse, its gravitational influence is strongest, and it can drive oscillations in the supergiant's extended atmosphere, the kind of long-period brightness variations that look, from a distance, like pulsation, but are not. When the companion sweeps through the dust-rich regions of Betelgeuse's circumstellar environment, it can clear pathways in the dust, allowing more of the star's light to reach Earth, which produces a brightening event. When it moves behind the star, or allows the dust to accumulate in the line of sight, the apparent brightness falls. This picture gained additional traction from the peculiar brightness recovery that followed the Great Dimming. After the catastrophic February 2020 minimum, Betelgeuse did not simply return to its pre-dimming brightness. By April 2023, it reached a visual magnitude of approximately 0.0, the brightest it had been in decades, sitting near the top of the rankings of naked-eye stars. visibly outshining its previous typical brightness. Amateur astronomers around the world reported Betelgeuse looking strikingly, almost uncomfortably bright. The star was, according to some measurements, nearly 50% brighter than its long-term average. This was not predicted by the single-star models. The surface mass ejection had disrupted the star's pulsation cycle and its photospheric structure. The models said the star should be in a period of uncertain recovery, not extraordinary brightness. But it fit naturally into a picture where the companion's orbital geometry, arriving at a specific phase of its 2,110-day cycle, was clearing circumstellar dust along the line of sight, allowing more of Betelgeuse's normal luminosity to reach Earth, making the already bright star appear dramatically brighter than its recent history would predict. The companion was not just explaining the long secondary period. It was explaining the whole arc of Betelgeuse's recent weirdness, the unusual dimming, the disrupted pulsation, the extraordinary subsequent brightening, the long baseline radial velocity anomalies that had accumulated for more than a century. It was a single explanatory object that resolved multiple outstanding problems simultaneously. In the history of science, when a single new hypothesis resolves multiple existing anomalies, that is the moment when confidence begins to tip from plausible toward probable. This was that moment for the companion hypothesis. But hypotheses, however elegant, are not confirmed by their explanatory power alone. For Betelgeuse's companion, confirmation required something else, a direct detection, and for years every attempt to actually see the companion had failed. The Chandra X-ray Observatory stared at Betelgeuse. The Hubble Space Telescope searched its surroundings. No companion appeared. The star's overwhelming brightness swamped every instrument that tried to peer into its immediate neighbourhood. Some researchers began to wonder whether the companion might be an object so intrinsically faint, a white dwarf or a neutron star, that even at maximum angular separation from the host star, it would remain below the detection threshold of any instrument then operating. And then, for a period of approximately 3 weeks in December 2024, the companion would be, according to the calculations, at its maximum angular separation from Betelgeuse, roughly 52 milliarc seconds, which is still extraordinarily close in absolute terms, but might just, with the right instrument on the right telescope, under the right atmospheric conditions, be enough. The team that set up to observe it, that December was taking a calculated gamble on the physics. There is a photograph from 1995 that I keep returning to in the course of writing this script. Not because it is a spectacular image, by current standards, it is modest and grainy, but because of what it represents. It shows Betelgeuse as a resolved disk, not a point source as every other star in the photographic history of astronomy had appeared, but an actual disk. A circular smear of light with surface features visible on its face, bright patches, a mottled texture, the unmistakable signature of a surface that is alive with convective activity. The resolution is low. This was Hubble's faint object camera, near the beginning of the instrument's scientific life. But the disk is real, and for the first time in human history, here was a star other than the Sun that had been directly imaged at its surface. The person responsible for those observations was Andrea Dupree. She is an astrophysicist at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts, and she has spent more than 3 decades in a sustained scientific relationship with Betelgeuse that is, by the standards of modern academic research, extraordinary in its depth and duration. In a discipline where careers are shaped by the pressure to publish frequently and to distribute attention across a wide range of problems, Dupree has maintained a focused, patient commitment to a single star that has produced some of the most consequential observational results in the modern study of stellar evolution. Her history with Betelgeuse began in earnest with those 1995 Hubble observations, the first resolved stellar disk image, but the work that directly preceded the Great Dimming was a 3-year Hubble program to monitor the structure of Betelgeuse's outer atmosphere in ultraviolet wavelengths, approved and funded in recognition of the star's scientific importance and the unique capability of Hubble's ultraviolet instruments to probe atmospheric layers that are far too hot to emit significantly at visible wavelengths. This program was, in the language of telescope allocation committees, a strategic investment in long-baseline monitoring of a unique and time-critical target. What she did not know when she wrote the proposal, naturally, was that she was scheduling front-row seats for an event that had never previously been observed in any star. The monitoring program began in January 2019. Through the spring and summer, the observations were routine, informative, scientifically valuable, but not alarming. Betelgeuse was behaving with its characteristic variability, its chromosphere and transition region showing the convective turbulence that makes it such a rewarding subject for ultraviolet spectroscopy. The ionized magnesium lines that Dupree's team was using as a diagnostic, measurements of singly ionized magnesium, Mg2, which traces the behavior of gas at temperatures of roughly 10 0 Kelvin in the star's outer layers, showed normal variation. The 420-day pulsation cycle was proceeding normally. Then came September 2019, and the first anomalous signal. Dupree has described the moment of realizing what the September data showed with a characteristic precision that carries more drama in its understatement than most scientists achieve with hyperbole. The magnesium ionization lines revealed material moving outward through the star's atmosphere at velocities inconsistent with the normal pulsation dynamics. The outflow was too fast, too dense, and concentrated in the wrong region of the disk. It came from the southeast. It was hot, substantially hotter than ambient, and it was moving. The October and November data confirmed the movement. By December, when the ground-based optical observations showed the star visibly dimming in its southern hemisphere, the connection between the Hubble ultraviolet data and the optical dimming became clear. She had, without intending it, captured the moments before the catastrophe began. We could see the effect of a dense, hot region in the southeast part of the star moving outward, she later told reporters. This material was 2 to 4 times more luminous than the star's normal brightness, and then, about a month later, the south part of Betelgeuse dimmed conspicuously as the star grew fainter. We think it is possible that a dark cloud resulted from the outflow that Hubble detected. Only Hubble gives us this evidence that led up to the dimming. This is precise science delivered in language that contains a quiet astonishment. She had the data that the entire astronomical community needed, the pre-event atmospheric signature that documented, for the first time, the sequence of events leading to a surface mass ejection in a star other than the Sun. The February 2020 Hubble observations added another piece. Even as the star was at its visual minimum, dimmer than it had been in recorded history, the ultraviolet data showed the star's outer atmosphere returning to something close to normal behavior. The photosphere was dark, the chromosphere was calm. This was the first observational confirmation that the dimming mechanism was external, a dust cloud between us and the star, rather than an internal collapse of the star's own energy output. Without the ultraviolet data, the distinction would have been far harder to establish. But the great dimming was not the end of Dupree's involvement with Betelgeuse's anomalies. It was, in retrospect, the moment that opened the deeper question, because the aftermath of the event, the disrupted pulsation cycle, the extraordinary brightening of 2023, the growing evidence for a long secondary period that demanded an orbital explanation, required not just a single observational campaign, but a sustained program of multi-wavelength monitoring that drew on every instrument she could access. In the years after 2020, she worked with data from Stellar, from the Tillinghast reflector, from Stereo, from AAVSO's volunteer photometrists, who provided nightly brightness measurements, and returned repeatedly to Hubble whenever Betelgeuse was accessible to the observatory's scheduling constraints, which, owing to the star's position in the sky and Hubble's solar avoidance zones, creates annual gaps in the coverage that require planning years in advance. Each instrument contributed a different wavelength window, a different atmospheric layer, a different physical diagnostic, stitching them together into a coherent picture of what a star had done to itself, and was continuing to do, required the kind of pattern recognition that only comes from intimate familiarity with the subject. I find in Dupree's career something that science journalism rarely has the patience to highlight. The value of staying with a problem. Modern research culture rewards novelty and breadth. The investigator who moves from topic to topic, publishing frequently on different subjects, tends to accumulate more papers and more citations than the person who decides that a single star contains enough physics to occupy an entire scientific life. Dupree's approach is different. Her 3 decades of focused attention on Betelgeuse gave her, when the Great Dimming arrived, a contextual depth that was simply unavailable to researchers who came to the star fresh. She knew where the baselines were. She knew which signals were normal variation and which were unprecedented. She knew that the September 2019 ultraviolet data was wrong in a specific and important way because she had years of normal behavior data to compare it against. Without that depth of familiarity, the pre-event atmospheric signal might have been logged and filed as an interesting anomaly. With it, it became the key piece of evidence in the reconstruction of a stellar catastrophe. And then, in 2025, the Hubble data she contributed to the companion search, searching for ultraviolet spectral signatures of the orbiting object in the far ultraviolet, helped define the constraints on the companion's nature. The observations did not directly image it, but they helped to characterize what it could and could not be, narrowing the parameter space in ways that guided the subsequent Chandra and Gemini observations toward a successful detection. The companion's discovery, when it finally came, was built on a foundation that included 3 decades of Hubble observations that Dupree had been instrumental in designing and executing. There is something quietly extraordinary about the scientific life her work represents. The star she first resolved as a disk in 1995, when many of the researchers who are now working on Betelgeuse were in primary school, is still revealing new things to her. Each surprise has been preceded by the kind of careful, patient accumulation of baseline data that makes the surprise legible. She did not predict the surface mass ejection. She did not predict the companion. She was in the best possible position to understand both when they arrived. That is what sustained scientific attention makes possible, and it is something that I think deserves more recognition in the stories we tell about how discovery actually works. The patience was about to be rewarded in ways nobody had entirely anticipated. Because the companion, when it was finally imaged, was not what the models had predicted. On December 9, 2024, a team led by Stephen Howell of NASA's Ames Research Center pointed the Alapeak Speckle Imaging Instrument on the Gemini North Telescope in Hawaii at the shoulder of Orion. The Alapeak instrument, named for a Greek word for fox, a nod to the instrument's ability to sneak up on faint objects hiding near bright ones, operates by taking thousands of extremely short exposures in rapid succession, then processing them to remove the blurring effects of Earth's atmosphere. Each individual exposure is too brief for the atmosphere to move appreciably, which means the image within each frame is, for a fraction of a second, as sharp as diffraction physics allow. Stack those frames carefully, filter out the atmospheric noise, and you can achieve resolutions approaching 18 milliarcseconds, enough, in principle, to detect a companion separated from Betelgeuse by roughly 52 milliarcseconds, the predicted angular separation at maximum elongation. December 9, 2024 was chosen because the orbital calculations, derived from more than a century of radial velocity, photometric, and astrometric data, predicted that the companion would be closest to its maximum angular separation from the host star on approximately December 6, 2024. The window was narrow. After December 6, the companion would begin to move back toward, and eventually behind Betelgeuse, where it would be hidden from direct imaging for another 2 years. This was the moment. The next comparable opportunity would not arrive until November 2027. The Alapeak data showed something at an angular separation of 52 milliarcseconds from Betelgeuse's centre, at a position angle of 115 degrees east of north. The detected object was approximately 6 magnitudes fainter than Betelgeuse, at a wavelength of 466 nanometers, deep blue in the visible spectrum. The separation matched the prediction. The position angle matched the prediction. The brightness difference matched the estimates. The detection was at 1.5 sigma statistical significance, a confidence level that the scientific community treats as tentative rather than confirmed, a level at which the result is worth reporting, but where prudent caution is appropriate until stronger confirmation arrives. But 1.5 sigma needs context. The Alapeak observations were pushing the instrument to its absolute limits, against one of the brightest and largest stars in the sky, in a detection regime where atmospheric noise and instrumental artifacts are genuine concerns. The fact that the detected signal agreed with the predictions, not just in one parameter, but in 4 independent parameters simultaneously: separation, position angle, brightness difference, and estimated mass, dramatically reduced the probability that the detection was coincidental. As Hal noted, this detection was at the very extremes of what can be accomplished with Gemini in terms of high angular resolution imaging, and it worked. This now opens the door for other observational pursuits of a similar nature. The companion was given a name by the research community almost immediately: Beetle Buddy, an informal designation that captured the spirit of the discovery without the formality of official IAU nomenclature. The more formal proposal, reflecting the Arabic etymological tradition from which Betelgeuse's own name derives, was Siwarha, an Arabic word meaning her bracelet. It is a name with a quiet aptness, a small object orbiting the great star in a tight arc, like a bracelet on a wrist. But what was it? This is where the discovery generated its second, separate surprise. The theoretical community before the detection had been broadly expecting one of 2 things: the companion's extraordinary elusiveness, despite decades of attempts to find it, suggested that it was intrinsically very faint. Very faint objects at stellar masses and ages are typically the husks of evolved stars, white dwarfs, the Earth-sized remnants of stars that have completed their hydrogen-burning lives and shed their outer layers, supported now by electron degeneracy pressure and slowly cooling over billions of years. Or neutron stars, the incredibly dense stellar corpses left behind by supernova explosions in stars of intermediate mass, city-sized objects with density surpassing that of an atomic nucleus. Both are genuinely difficult to detect in the optical, and both would fit the constraint of a companion that had been invisible through decades of optical observation. A white dwarf companion would have implied that the Betelgeuse binary system had already produced one supernova event in its history, that the 2 stars had been part of a system long enough for the initially more massive companion to have evolved and died. A neutron star would have implied the same, but with a more violent end state. The Carnegie Mellon University X-ray study, led by Anna O'Grady, and published in October 2025 in the Astrophysical Journal, used the Chandra X-ray Observatory to probe Betelgeuse's immediate neighbourhood for the 11. 5 hours of combined exposure time across 7 separate observing runs. The logic was specific. White dwarfs and neutron stars produce distinctive X-ray signatures under certain conditions, and the Chandra observations could place tight constraints on the X-ray luminosity of anything in the companion's expected vicinity. What they found was inconsistent with a white dwarf or neutron star. The X-ray constraints pointed instead to a young stellar object, a pre-main sequence star, with a mass between approximately 0.5 and 1.5 solar masses. This was not what anyone had predicted. A young stellar object, in the vocabulary of stellar astronomy, is a star that has not yet fully contracted to the point where it has ignited sustained hydrogen fusion in its core. Pre-main sequence stars are still in the process of collapsing under their own gravity, heating up as they do so, still drawing on gravitational energy rather than nuclear energy as their primary source of luminosity. They are young, genuinely young, in the cosmic sense, and they have a characteristic spectral energy distribution that differs from main sequence stars and from degenerate remnants. Betelgeuse is approximately 10 million years old. How can it have a companion that is younger than itself? The answer is that it cannot. The companion is also approximately 10 million years old. It formed from the same molecular cloud, at roughly the same time, as Betelgeuse itself. The apparent paradox is resolved by mass. Betelgeuse at 16, 5 to 19 solar masses, is a heavy star, and heavy stars evolve fast. In 10 million years, it has burned through its hydrogen, expanded to supergiant dimensions, and is now burning helium in its core, approaching the final stages of its evolution with the urgency of a star that has always burned too hot. The companion, at perhaps 1.5 solar masses, has lived 10 million years barely noticing the passage of time. At that mass, the main sequence hydrogen-burning lifetime is roughly 10 billion years, which means the companion at its current age has not even reached the beginning of its adult stellar life. It is still contracting, still warming. In the language of the Hertzsprung-Russell diagram, it is descending toward the main sequence on what astronomers call the Hayashi track, that slow, luminous journey from protostellar contraction to nuclear ignition that takes a star of this mass several more tens of millions of years to complete. Two stars, born together from the same cloud, now in completely different chapters of their lives. One is a dying giant, millions of kilometers across, glowing red with the heat of helium fusion in its core and preparing, on a timescale of tens of thousands of years, for the final gravitational collapse. The other is a young star, still arriving, still finding itself, not yet old enough to have lit its own nuclear fire in any sustained sense. They orbit each other at a distance of roughly 4 astronomical units, 4 times the Earth-Sun distance, which means that Betelgeuse orbits not in open space, but inside the extended outer atmosphere of its companion. It is a star embedded in another star's gas. The fate of this arrangement is not in doubt. Betelgeuse is losing mass continuously through its stellar wind, and as a red supergiant, that mass loss rate is orders of magnitude higher than that of a main sequence star, roughly 30 million times higher than the Sun's own stellar wind output, and punctuated by episodic events like the 2019 surface mass ejection that can strip away additional material in single events. The mass loss causes Betelgeuse's outer envelope to expand. The tidal forces within the binary system will draw the companion progressively inward as the system loses mass and the orbital dynamics evolve. Within approximately 10,000 years, a moment in cosmic terms, a blink even in the scope of recorded human civilization, Betelgeuse will have consumed its companion. The smaller star will be tidally disrupted and absorbed by the giant before it has had the chance to ignite its own hydrogen core. It will never grow up. It will be eaten, and then, in the absence of the companion's tidal torque, the angular momentum budget of the system will change. The dynamics of mass loss will evolve in ways that current models are only beginning to explore, and Betelgeuse will continue its journey toward the final collapse. Perhaps sooner, perhaps later, as a result of what the companion has done to it. I find this genuinely difficult to sit with. There is something in the image of a young star, not yet fully formed, orbiting inside the atmosphere of the giant that will eventually consume it, that captures something about the universe's relationship with time and scale that no other discovery in recent stellar astronomy has managed to articulate so directly. The companion does not know it is being consumed. It has no knowledge of its situation. But the knowledge is there in the physics, written in the orbital mechanics and the mass loss rates, and the outcome is not in doubt. In 10,000 years, Betelgeuse will be gone. The discovery of Betelgeuse is, in scientific terms, considerably more consequential than its status as a confirmation of an existing hypothesis might initially suggest. Confirming that Betelgeuse has a companion is significant, but what that companion implies. For models of stellar evolution, for the interpretation of a century of Betelgeuse observations, for the broader understanding of red supergiant behaviour, and for the question of when and how Betelgeuse will eventually die, is a set of revisions that reaches into nearly every corner of massive star astrophysics. This is the Betelgeuse implications problem, and it is one that the community is still in the early stages of working through. Begin with the pulsation data, which forms the scientific foundation of almost everything we thought we knew about Betelgeuse's evolutionary state. For decades, astronomers had used the star's pulsation periods as a diagnostic tool for its internal structure. The reasoning is the same as the medical use of heartbeat patterns. A pulsating star oscillates at frequencies determined by its mass, radius, and density profile. And by measuring those frequencies carefully, you can infer properties of the interior that are not directly observable. The technique is called astroseismology, and for compact, well-behaved stars on the main sequence, it has been enormously productive. For red supergiants, the application is murkier because the outer layers are so vast, so loosely bound, and so dynamically chaotic that the clean astroseismic signatures that allow precise inversions of stellar structure are badly blurred. This murkiness was already a problem before the companion was found. The companion introduces a new layer of complexity. The gravitational influence of an orbiting body at 4 astronomical units, with a 2,110-day period, will excite oscillation modes in the supergiant's extended atmosphere that are not intrinsic to the star, but are driven externally. If some fraction of Betelgeuse's observed variability, including, potentially, some components of what had been attributed to the fundamental mode or overtones of radial pulsation, is actually driven by tidal forcing from the companion, then the astroseismic inferences drawn from that variability are systematically wrong. The model of the star's interior, built from the pulsation data, needs to be rebuilt, incorporating the binary dynamics. This has direct consequences for the most consequential question in Betelgeuse studies. How far along is this star in its evolution, and how long does it have before the final core collapse? The range of estimates here is, it has to be said, genuinely remarkable. Conservative models based on the assumption that Betelgeuse is a single star in the early helium core burning phase suggest it may have between 10,000 and 100 Zuzoran years remaining before core collapse. A 2023 study led by Hideoki Sayo and colleagues proposed a more provocative interpretation. If the long secondary period is interpreted not as an orbital signature, but as the fundamental mode of radial pulsation, it would imply a much larger stellar radius, and would place Betelgeuse in its carbon core burning phase, a stage that lasts only a few hundred years in stellar evolution models, and which, if correct, would suggest the supernova could occur within a human-relevant timescale. The study suggested the star might have less than 600 years of carbon fuel remaining. This interpretation has been challenged. A 2023 rebuttal by Laszlo Molnar, Meredith Joyce, and Xingqi Liang pointed out that the stellar radius implied by the fundamental mode interpretation of the long secondary period is incompatible with angular diameter measurements. You cannot reconcile the size of the stellar disk on the sky, which has been measured with milliarc-second precision using interferometric techniques, with a radius large enough to produce a 270-day fundamental pulsation period. The geometry does not work. Their conclusion was that the long secondary period is not the fundamental mode, and therefore does not carry the evolutionary implications that Sayo's team had drawn from it. Now, with the companion hypothesis confirmed by direct imaging, the debate takes a new shape. The long secondary period is most plausibly orbital, not pulsational. This removes the basis for the argument that Betelgeuse is in its carbon-burning phase, which is reassuring in the sense that the imminent supernova scenario loses its most dramatic observational support. But it does not return us to the comfortable pre-2019 model because the companion's existence changes the stellar evolution calculations in other ways. Red supergiant mass loss. the continuous shedding of outer material through stellar winds and episodic ejection events is one of the most important and least precisely constrained processes in stellar evolution models. The rate at which a star like Betelgeuse loses mass through its wind affects the size of the hydrogen envelope remaining at the time of core collapse, which in turn determines the type of supernova it produces, the mass of the compact remnant it leaves behind, the energy of the explosion, and the composition of the ejected material. Get the mass loss rate wrong, and your supernova model is wrong. The companion's presence will affect mass loss, because the companion's gravitational tides can drive additional mass loss through the enhanced stellar wind and through periodic episodic events, perhaps events very like the surface mass ejection of 2019. This raises a genuinely uncomfortable possibility. The 2019 surface mass ejection may not have been a random event caused by an unusually energetic convective plume. It may have been tidally triggered, driven, at least in part, by the gravitational forcing of the companion during a particular phase of its orbit. If the companion was, in December 2024, at its maximum angular separation, having recently completed its closest approach passage on the predicted orbital timeline, then the timing of the 2019 SME occurring roughly one full orbital period before the 2024 maximum separation falls naturally into a picture where the companion's closest approach passage coincided with or triggered the ejection event. This is, as of mid-2026, not definitively confirmed. It is a hypothesis supported by circumstantial timing evidence that will need to be tested against detailed orbital models and multi-wavelength observations over the next several years. But if it proves correct, it changes the interpretation of the 2019 event from a singular catastrophe, the once-in-a-lifetime blowout of an aging star, to a potentially recurring phenomenon, one that happens on the 2,110-day orbital cycle. The next closest approach of Betelgeuse to Betelgeuse would then be a predicted event, with a specific geometry, a specific timing, and a specific window in which enhanced mass loss and potential atmospheric eruptions might be expected. The astronomy community would, in that case, be watching Betelgeuse with a scheduled alarm. There is also the question of what the binary history means for Betelgeuse's spin. The anomalously fast rotation rate, 5 kilometers per second, 2 orders of magnitude above single-star predictions, requires an angular momentum source. The leading candidates are two, either a past merger with a smaller companion, which would have injected angular momentum into the surviving star, or tidal spin-up by the current companion, which transfers orbital angular momentum to the supergiant's rotation over millions of years of close orbital evolution. A past merger would mean that Betelgeuse has already consumed at least one companion, and the Betelgeuse that exists today is a second companion in a system that has a history of orbital evolution and mass transfer. A spin-up by the current companion would mean that the 5 km/s rotation rate is the cumulative effect of 10 million years of tidal interaction with the same object now detected at 52 milliarcseconds. Distinguishing between these scenarios matters, because they produce different predictions for the star's future. A single merger history is different from an ongoing binary interaction. The internal structure left by a past merger, the angular momentum distribution within the stellar interior, the mixing of material between regions of different composition, would produce different pulsation frequencies, different convective properties, different mass loss rates, from a star that has never undergone a merger. Teasing out which scenario is correct requires the kind of detailed interior modelling that pushes even the best stellar evolution codes to their limits. But there is a third possibility that has entered the discussion, one that carries the most dramatic implications of all. Some models of the binary evolution suggest that Betelgeuse's orbit will not remain stable as Betelgeuse continues to expand and lose mass. The orbital dynamics of a binary system in which one member is growing in radius while losing mass are complex and non-intuitive. Under certain conditions, specifically when the mass-losing star loses mass faster than the orbital dynamics can accommodate, The orbit does not widen, as simple conservation of angular momentum might suggest, but narrows. The companion spirals inward, and if the inward spiral proceeds faster than current estimates allow, the companion could be engulfed not in 10,000 years, but on a shorter timescale, perhaps altering the final stages of Betelgeuse's evolution in ways that current models simply have not accounted for. An engulfed companion, absorbed by the supergiant's outer envelope, would inject a burst of angular momentum and orbital energy into the stellar interior. That energy input could alter the convective structure of the envelope, change the mass loss rate, and, in some models, actually affect the timing of the final core collapse. If a companion engulfment event can accelerate or delay the detonation by even thousands of years, and if Betelgeuse is already within that uncertainty range of a potential supernova, then the binary nature of the system becomes a direct input to the prediction of when the night sky will next contain a star brighter than Venus, blazing steadily in the constellation of the Hunter, visible in full daylight. There is also the question, less immediately dramatic but scientifically significant, of what Betelgeuse means for other red supergiants. The two most obvious comparisons are Antares, the red supergiant in Scorpius, and Arcturus, the orange giant in Bootes. Both display long-period variability that has been attributed, with varying degrees of confidence, to internal oscillations. Both are sufficiently close and sufficiently large that resolving any companions they might possess is in principle feasible with existing or near-future instrumentation. The Arxiv paper by Priya Hassan notes this directly. The discovery of Betelgeuse opens up the possibility of RSG stars like Betelgeuse, Antares and Arcturus, which both have extra-long variability periods, to possibly have a hidden companion as the reason for their variability. If long-period variability in red supergiants turns out to be, systematically, a signature of binary companions rather than intrinsic pulsation, then a significant fraction of the stellar evolution models built on those variability periods need revision, not just for Betelgeuse, for the entire class. This is what makes the discovery of Betelgeuse more than a curiosity about a famous star. It is potentially a paradigm revision in how we understand the late stages of massive stellar evolution, a revision that touches the mass loss rates that determine supernova yields, the binary fractions of massive stars, the interpretation of long-period variability across the entire red supergiant population, and the question of how often the explosions that seed the universe with heavy elements are shaped, in their final moments, by the presence of a companion that nobody knew was there. And behind all of this complexity, there is a fact that continues to resist clean resolution. We do not know when Betelgeuse will explode. The range of estimates spans from decades to 100,000 years. The binary discovery has not narrowed that range. In some respects, it has widened it by introducing variables that current models cannot precisely account for. The most candid summary of the current scientific state is that we are watching one of the most intensively studied stars in the sky, with the best instruments ever built, and we cannot predict its fate on a timescale meaningful to human civilization. I find this honest uncertainty more compelling than any false precision would be. Science rarely offers tidy resolutions. What it offers, at its best, is a clearer view of what we do not yet know. November 2027. Mark it somewhere if you find dates meaningful. It is the next time that the orbital geometry of the Betelgeuse binary system will place Betelgeuse at or near its maximum angular separation from its host star. The next observational window in which direct imaging might succeed in confirming and refining the 2024 Gemini detection. If the observations succeed and the companion's position, brightness and separation match the orbital predictions with high statistical significance, the 1.5 sigma tentative detection of December 2024 will graduate to confirmation. The binary nature of Betelgeuse will be established beyond reasonable doubt, and the long Basseline program of observations needed to fully characterize the orbit, its precise inclination, its eccentricity, the companion's actual spectrum and temperature, can begin in earnest. if the observations fail, if the companion does not appear where the models predict it should be, at the brightness the models require, then the picture becomes considerably more complex. A non-detection in November 2027 would not immediately falsify the companion hypothesis, because there are instrumental and atmospheric reasons why a 1.5 sigma detection might not reproduce, and because the orbital models themselves carry uncertainties that could place the companion in a somewhat different position than predicted. But it would delay confirmation and force a reassessment of the orbital parameters. The community would wait for the next maximum separation in 2029 and begin again. Meanwhile, the program of multi-wavelength monitoring that has characterized Betelgeuse studies for the past several years will continue and expand. The James Webb Space Telescope, which has already demonstrated an ability to map infrared emission from stellar surfaces and their immediate environments with unprecedented resolution, is a natural instrument for tracking the evolution of the circumstellar dust in Betelgeuse's vicinity, mapping the material ejected during the 2019 surface mass ejection as it continues to move outward, and searching for the thermal signature of the companion in near-infrared wavelengths where the brightness contrast between the two objects is somewhat more favourable. Webb observations of Betelgeuse were proposed within months of the companion hypothesis gaining traction, and results from those programs will add new constraints to the picture in the coming years. The ALMA interferometer array in the Atacama will continue mapping the radio emission from Betelgeuse's photosphere and inner atmosphere, providing the highest resolution images of any stellar surface outside the solar system. ALMA data has already confirmed the presence of large-scale convective structure on Betelgeuse's surface, the 2 to 3 massive convection cells that dominate its dynamics, and as the star continues its post-SME recovery, the evolution of that convective structure will be one of the most direct diagnostics of whether the interior is returning to its pre-2019 state, or whether the ejection event has permanently altered the star's convective behaviour. The question of the pulsation recovery is particularly consequential. As of the most recent published data, the 400-day pulsation cycle that governed Betelgeuse observations for almost 200 years has been disrupted and has not fully recovered. Whether it returns to its pre-2019 pattern, demonstrating that the surface mass ejection was a recoverable perturbation, or whether it settles into a new, different pulsation state, will tell observational astrophysicists something important about the coupling between a supergiant's atmosphere and its interior. If the pulsation changes permanently, it suggests that the ejection event altered something fundamental about the internal structure, perhaps by changing the mass distribution in the outer layers, or by altering the convective patterns that drive the Kappa mechanism oscillation. If it recovers, it suggests the star's interior is more resilient than the violent surface event implied. There is also the question of what comes next, in the orbital evolution of the binary. If the companion's 110-day orbit is tidally decaying, if Betelgeuse's expanding radius and continuous mass loss is drawing the companion inward rather than pushing it outward, then the timeline of 10,000 years to engulfment may be optimistic. Some models of binary evolution in high-mass ratio systems suggest the engulfment could happen faster. Conversely, if the mass loss from Betelgeuse is predominantly driving material outward along the orbital plane, as some models of mass transfer in close binaries predict, the companion's orbit might be widening, and the 10,000-year timeline might be pessimistic from the companion's perspective. Distinguishing between these outcomes requires precisely characterized astrometric positions of the companion over multiple orbital periods, which means observations spanning at least one, ideally 2 or 3, complete 110-day cycles. The observational program needed to answer this question definitively will take until at least 2030 to produce meaningful results. And then there is the supernova itself, the question that hovers over every discussion of Betelgeuse with an urgency that no other star in the human sky quite generates. When Betelgeuse goes supernova, its visual magnitude will briefly reach somewhere between 8 and 10 at current estimates. For comparison, the full moon has a visual magnitude of approximately 12.6. A Betelgeuse supernova would not match the full moon in brightness, but it would comfortably exceed Venus at its most brilliant, and would be visible in daylight. At night it would cast shadows. It would remain naked-eye visible for weeks or months, even after the initial peak, as the expanding cloud of ejected material continues to glow with the energy of radioactive decay. It would produce a neutrino burst detectable by underground detectors around the world, arriving hours before the visible light, giving a few hours of advance warning that something extraordinary was happening at Orion's shoulder. And it would leave behind, at the system's centre, either a neutron star, an Object 1, 5 times the mass of the Sun compressed into a sphere roughly 20 kilometres in diameter, or, depending on the precise mass of the collapsing core, a black hole. Betelbuddy would not survive a Betelgeuse supernova. The explosion releases approximately 2 times Talon 53 ergs of energy, almost entirely in neutrinos, with roughly 1% of that energy going into the visible explosion and the kinetic energy of the ejected envelope. At an orbital distance of 4 astronomical units, the companion would be engulfed by the expanding shockwave before it had any time to respond. What would happen to the companion in that case is not straightforward to calculate. It might be dissipated entirely by the explosive interaction with the supernova shockwave. It might be stripped of its outer layers but leave a surviving core. It might be accelerated to escape velocity and ejected from the system as a runaway star, carrying the imprint of the event in its velocity and chemical composition for billions of years. These are questions that stellar astrophysicists are actively modelling, because the answer matters for what the binary's post-explosion remnant looks like. Whether the Betelgeuse system eventually becomes a solitary neutron star or black hole, or whether it produces a compact binary, a pair of gravitationally bound stellar remnants whose eventual merger, billions of years hence, might itself be detectable from Earth as a gravitational wave event. What will the sky look like to human observers on the night Betelgeuse explodes? It will not be a slow fade, a gentle brightening like a dawn that comes early. It will be sudden. A star that was orange-red and familiar in Orion's shoulder will, over the course of hours, become something the night sky has not contained within recorded human history. A fixed, blazing point of light that does not rise and set with the stars but burns there, steady and relentless, through day and night. Navigation apps will need to be updated. Photographers will line up to capture the shadow of their hands on sunlit walls, cast by a stellar explosion that occurred more than 700 years before anyone alive today was born. For months, perhaps more than a year, the remnant will be visible. Children alive now will tell their grandchildren about the night the sky changed. This will happen. The certainty is not in doubt. The uncertainty, the frustrating, humbling, honest uncertainty, is only in the timing. There is a thought that I find it impossible to entirely set aside when I spend time inside the Betelgeuse story. It concerns the relationship between the light we receive and the events that produced it. The light currently leaving Betelgeuse will take approximately 700 years to reach Earth. The light we are seeing tonight, that coppery point in Orion's shoulder, left the star around 1325 CE, in the era of Marco Polo of the 100 Years' War, when the Black Death was beginning its first devastating wave across Eurasia. The star we observe through our telescopes, the star whose dimming alarmed the world in 2019, the star whose companion was imaged for the first time in December 2024, that star, as it actually exists in the present moment of the cosmos, is unknowable to us. It has already, in the light we haven't received yet, done things we have no knowledge of. It may already have exploded. The neutrinos from that explosion, if it has happened, are already racing toward us at just under the speed of light, and the photons, the visible light, are not far behind. We would not know until they arrive. We will not know until we receive the signal. I think about what it means to watch something you cannot fully observe. The astronomers who have spent careers studying Betelgeuse, Dupree, McLeod, Goldberg, O'Grady, Howell, and hundreds of others whose names appear in the acknowledgements sections of papers rather than the headlines, have all been working with information that is 700 years old. The story they are piecing together happened in the 14th century, in our terms. The companion was orbiting then. The convective cells were heaving then. Whatever the star's interior is doing right now, in the actual present of the universe, is beyond our reach. We are, all of us, archaeologists of the recent cosmic past, and yet this is not a limitation that makes the science less valuable. It makes it more remarkable, because from 700 years of old light, we have reconstructed the internal dynamics of a star more than 100 solar diameters across. We have detected, in a signal buried in the radial velocities of a star too far away to walk to in 10,000 human lifetimes, the gravitational signature of a companion smaller than our own Sun, orbiting inside a star's extended atmosphere. We have found a star that has never yet lit its own nuclear fire, circling a star that is preparing to die. We have, in other words, done what science does when it is working at its best. Extracted from incomplete, imperfect, ancient information a picture of reality that we had no right to expect we could see. Betelgeuse is not finished surprising us. The 2027 observations will bring new data. The Webb infrared surveys of the circumstellar environment will bring more. The next pulsation cycle data will either confirm or complicate the recovery narrative. The orbital mechanics will evolve in ways the models are still learning to track. And somewhere in the depths of the star, in the silicon burning shell, or the oxygen burning shell, or the core itself, where iron is perhaps accumulating, processes are underway that will eventually produce the most energetic individual event visible to the naked human eye in recorded history. We do not know when. We know it will happen. There is a peculiar dignity in that uncertainty. It is not ignorance. It is the frontier of knowledge, and the frontier looks like this: a warm copper star, a hidden companion, a disrupted heartbeat, a century of accumulated data, and an explosion that has not yet arrived. Every night you look at Orion's shoulder, you are watching one of the universe's great countdowns without knowing how much time remains on the clock. You are, in the same glance, looking at a star that blew its top somewhere around the year 1319, a companion discovered in 2024, and a death that could announce itself tomorrow or 100 millennia from now. We keep watching because the watching matters, because the record we build today, the AAVSO observations, the Hubble spectra, the Gemini speckle images, will be the archive that the scientists of 2124 or 2224 used to understand what we were seeing. We are not the last to watch this star. We are part of a chain that stretches back to medieval Arab astronomers and Australian Aboriginal sky watchers, and forward to observers whose telescopes we cannot imagine, who will see Betelgeuse's remnant with eyes we do not have. The light is still travelling. The story is still unfolding. And the next chapter, whenever it arrives, will be visible to anyone on Earth who happens to be looking up.